Ellipses.
8.2 notes.
You caught me right after I took a bite of apple. I'm so sorry.
I do that all the time. All right, so an ellipse is a set of all points of planes whose distances from two fixed points of the plane have a constant sum. So those are going to be our foci,
right?
Which is plural of focus,
right?
And it's real. I don't know how you pronounce it for sure. I like to say foci.
I do this. I use both.
Yeah, so that's a tough one, but just as long as you get your point across, and it's not focuses.
Yeah, don't say focus. That's not what it is.
Okay, so if you take the distance, but like if you have your two foci and like you draw to a point, at any point, if you add those distances together, they should be the same thing.
Wow.
So that's kind of a neat concept.
You could do an ellipse with a piece of string, right? And two tacks.
And two pieces of... No, yeah, you're right.
Take a piece of string.
Yeah, you would put two tacks down.
Right.
And wrap the string around and then put your pencil at where it's the tightest.
Right.
And then just make it draw in an elliptic fashion.
It's kind of a cool thing.
That is kind of a cool thing. So some more vocabulary. The line through the foci is the focal axis.
That's an important one to remember too.
Yes. The point on the focal axis midway between the foci is the center, which, I mean, it's usually pretty obvious what the center is.
The center is the center.
Yeah. The points where the ellipse intersects its axis are the vertices, and so whichever one's the focal axis is actually is it the longer one normally, right? That's the focal axis, is the way that it's longer.
Yes, yeah, the focal axis has to be longer with the ellipse.
And so the vertices are the points at the end of the ellipse.
Right.
On the long,
which would also, we
direction.
could also call it the major axis, as it were.
Right. The major axis is the longer axis. The minor axis is the shorter axis.
And you might see also in texts where the other part of your ellipse, not the major, but the other smaller distance from center to the point on the curve, sometimes is referred to as a minor vertex.
A minor vertex. Oh, okay. Yeah. So that you have vertices, and then the other direction you'd have minor vertices.
Or sometimes co-vertices or something like that.
Okay, that makes sense. So we have a box and an example of what an ellipse looks like on our notes. And so this box, just like the boxes for parabola, are going to be super helpful for our problems.
Super helpful to the infinity power.
Right. So the only difference between these, and this is really just kind of, just to specify a little bit of a difference here, is that basically A is going to be the bigger axis. So A is going to be greater than B.
Every single time with an ellipse. Period. End of story.
Right. So they may not actually, in the book or while we're doing stuff, we may not actually write y squared first ever, but addition is commutative.
Right. So you could write it
in either order. And so this second column here is where the bigger number is underneath the y.
Right.
And so that's what's going to make this case happen, which would give us an ellipse that is skinnier.
Right.
It's looks like a cucumber, perhaps.
Right.
All right, so how about on example one, let's find the vertices and the foci of the given ellipse.
So first off, please notice that for an ellipse, you have to equal 1.
Yep, that would be standard form. So how do I change a 36 to a 1?
You divide by 36.
Brilliant. So if we divide one thing by 36, we got to do it to everything.
Yeah, that's totes brilliant, by the way.
Thanks.
Yeah.
And so this may look challenging to simplify, but I like to think of it as 36 divided by 4 gives us 9 on bottom.
Right.
And for the most part, that will work out. Every now and then you'll end up with a fraction on the bottom, which is uncomfortable, but it can happen.
And we'll probably discuss how to deal with the fraction on the bottom.
Hopefully.
Yeah.
Hopefully. So this is a case where the x has the bigger number underneath. So this is the first column.
The A is 3.
So the A is 3.
Why is it 3? Because you have to take the square root of the 9.
Because this is actually A squared.
Right.
And so B here would be 2.
Right.
Okay, and then what's important here is a Pythagorean relation for this, which we all know the Pythagorean theorem, but for ellipses, we instead of adding a squared plus b squared, we have to subtract a squared minus b squared, and that will give us c squared. And c is like a special helpful number for the foci, basically.
Yes, it tells you, c actually will tell you how far from the center of your ellipse the focal points are to be located. So
right.
Square root of 5, although not a a number I carry around in my back pocket, I know about where that is.
It's somewhere between 2 and 3?
Yes.
So our vertices, if we look at our chart over here, our vertices are at plus or minus a comma 0. A is 3, so
Plus
they're
or
at
minus 3.
plus or minus 3,
And
comma
0.
0. Our foci,
Are plus or minus the c part then.
right, so plus or minus c means we'll have
Plus or minus the square root of 5.
comma 0. And the important thing is that because the bigger number was under x, that's where we stuck these values was with
Right.
x. If the bigger number had been with y,
Then
we
you
would
can
have put it
put
with
them all
y.
with y. Yep.
So,
The center of this guy, BT dubs,
uh-huh,
is at the origin.
yes. at
Because we're not
0, 0.
adding or subtracting anything
to our
to
x and
x1.
y's. Yeah. All right, example 2. Find an equation of an ellipse with foci 0, comma negative 3 and 0, comma 3, whose minor axis has a length of 4. Sketch the ellipse and support your sketch with a
I
graph.
already know what B and C are. I can tell you right away without doing any math.
Okay, and why don't you also tell us your thought process there for finding B and C?
Well, here's the deal. If for finding C, that's the distance from the center to the focus. So if I go 3 one direction and 3 another from the origin, then my C value would have to be 3 because the sign changed. So I just went from positive 3 to negative 3.
Absolutely.
Okay.
So this is a plus or minus C
Right.
situation.
Right. Plus or minus C.
That means C is 3.
Yeah.
Now how about B?
B then, if I know that, that must have been my spelling there. That linked. That's
Yeah.
got to be a Scott Hazelwood oopsie there.
Whoops.
So if the minor axis is just 4 units long,
Uh-huh.
then that would be half of that. Then would be the B value because the distance from the center to that co-vertex, that minor vertex, is 2.
That's right. So B would have to be 2.
Take a picture of the picture.
Yeah, so I can fix that.
All right.
All right, so B would be 2 because if it has minor, that's twice as long as the length of our semi-minor, which is
Right.
what B
Right.
is, right? So we had to divide that by 2. So we know what C and B are. The other things we'll need for an equation are A. Actually, it's the
yeah.
only other thing we need. So we use
That's
this
the only other
Pythagorean relationship, A squared minus B squared equals C squared. So I'm adding 2 squared over so that I get 9 plus 4, which is 13. And if I square root both sides, that gives me A equals,
Plus or minus the square root of 13. Now, I know the square root of 13 can be a little bit of a sticky, tricky thing.
well,
So
it's between 3 and 4.
You just have to figure out, 9 is the square root that we know to be 3. 16 is the square root we know to be 4. So we're right in between those.
That's right.
So
Now we're set up to do our equation, and no matter which one is the bigger axis, typically we do write x squared first. But A, which is the square root of 13, which is our bigger thing, has to be underneath y because of the way our foci is
right,
written.
wherever the focal numbers go, that's where your A's and B's. That's where your A needs to go.
Right, and so our a squared, which would go underneath y, is square root of 13 squared, which is 13. Right, so we
Right.
technically really only needed to solve for a squared,
Right.
which was 13.
But when we graph it, we'll need that square root part.
Right, so b goes underneath x, 2 squared is 4, and so that right there
There's
is
your
our
equation.
answer. Now, I think graphing ellipses is pretty simple,
I agree with you.
okay? And so you just make your x and y axis, and you draw some lines.
And we're centered at the origin on this one,
Right.
so that always helps.
And so here's what you do is you go left and right
2 units.
2 units because that's the square root of 4. So I make a mark to the left and to the right 2 to start me off, and then we're going to go up and down somewhere between 3 and 4. So
A little bit closer to 4 than to 3, but not much. No, not that close.
Oh, hush.
Oh, no.
And then you connect them in an elliptical fashion,
Sort of like an American football,
or like
an
an
oval.
Easter egg kind of ish. There's lots of things you could pretend that that's the shape of. But
That's a
there's
really
our
good
ellipse.
ellipse, by
Well,
the way.
thank you.
Yeah.
I've been practicing.
I can tell.
Thanks. Example 3, now we're talking about ellipses with not a center at 0, 0. Their center is at HK, and that should look familiar. We talked
We
about
just did
parabolas
HK.
with HK.
Yeah.
And so just like before, if it's in parentheses and you pull it out of parentheses to find h and k, you change the sign because it's
The
minus
super
h
secret
minus k.
opposite society.
Right. So we're going to use this, and again, like the only difference between these is which is the bigger number. Is
Right.
it under x or is it underneath y?
Right.
So
same rules apply as what we did on the first slide.
absolutely.
Yeah.
Find the standard form of the equation for the ellipse whose major axis has endpoints -2, -1, and 8, -1, and whose minor axis has length 8.
Okay, you first.
Well, I just remembered that I had forgotten that I remember. Okay, on example 2, just before this,
Yes.
it said check with your grapher. And so I just thought I'd throw out there that when you put it into your calculator, if it's 83 or 84, remember you have to solve for y.
Right.
And that moment when you square root, remember to plus
Oh,
or
yeah,
minus.
it's got to be plus or minus.
And do not simplify those square roots because
No.
then you'll end up with something
No,
bad.
don't simplify the square roots. And you might have to change your window a little bit too on the 83 and 84 so that your ellipses actually connect.
Yes, yeah, you might have to mess with it some because a lot of times it won't connect them all
Yeah.
the way,
And
even though you know
even though
they should be
They
connected.
are connected. So if you turn into us an unconnected graph,
I mean, that's just silly.
well, we might have to require some sort of painful procedure.
Okay, so now example 3. What were you going to say about
Well, what I was going to
example
say is
3?
I already know what B is going to be.
Okay.
Well, it's half of the minor axis.
Half of the minor axis.
So it's going to be 4.
All right, so B is 4.
And now I have to pay attention here to figure out what A is. It tells me that the major axis has endpoints -2, 1, and 8, -1. The x coordinate changes here, which tells me that my ellipse is going to have the larger number under x.
Yes, because of what we've got going
Right.
on right here.
Right.
So
So
the
if I do
vertices
where
are-
I stop, which is 8, minus where I start, which is -2, and divide that in half, then that should give me the length of my major axis.
So A should be 5.
Yeah.
And that's because of the idea that, like, if you wanted to draw this, we've got over here at -2, -1, like, you know, we've got 1 vertices here, 3, 4, 5, 6, 7, 8.
That's way over
Yeah.
there.
So how long is that axis? Well, you'd actually add the two numbers together, ignoring
Right.
negatives. So
Right.
you get 10, and you divide it in half, and you get 5. So that's A and B, and that's really all we need H and K. And so this is where, since they gave us the vertices, our vertices are H plus or minus A comma K.
Right.
And so
So the K part never
the
changes.
K part,
So we know what that is.
right, the K is -1. So H plus A has to equal one of those numbers, and H minus A has to equal the other one. So it's probably going to be this situation. So we know what A is. A is 5, and so we can just throw that in there and then solve, and then look at what that gives us. So subtract the 5 over and you get 3.
Yep.
Add the 5 over, you get 3.
Hey, you get 3 on both.
Which is good, because H can't be two different things.
Be really weird if one of those wasn't.
Right, so now we can set up our equation. X minus H squared plus Y
Minus
K. So that's minus a
Minus
negative.
a minus.
Underneath X is A, we said, because it's
A
the bigger
squared,
axis.
so 25.
Yes. Oh. Whoop.
Man, good save.
And underneath Y is B squared, so that's 16, and it equals 1.
Bingo, bango, bongo.
Now, yeah, and if you're drawing this out, then which it doesn't ask us to, our center point is right here. We go left and right 5, up and down 4.
So it's almost a circle-y, but
That's
not
pretty
quite.
close. And then you just draw your ellipse
You know, the
around.
planets tend to fall an elliptical course around the sun.
And you know what? I was actually told recently in a class that the sun is not at the center; it's at the foci.
You don't remember talking
I
about
don't
that
remember
last
talking
year
about that
when we
last
did?
year. No,
oh
I don't.
My goodness.
So yeah. Interestingly enough, the sun's not actually the center.
So if you had just paid attention
I
in
just paid
class last
attention.
year, let me just help you out real quick. You just go ahead and start.
All right, so example 4. Find the center, vertices, and the foci of the ellipse. So let's start with the center, which is H comma K.
Notice that the sun is at a focus of the orbiting object.
Go figure.
Yeah. And perihelion is the closest point And at the Elion...
Well, we'll get to that in a second. The center is negative 2 comma 5, which means we know h and k.
Maybe I did this lesson last year.
Maybe. So underneath x here, this is the smaller number, which means that b is 3. This is the bigger number, which means a is 7. So when we look at this, we're going to look at the second column because that's where a is bigger. And so our vertices, we take our center point and we're adding a to the k value and subtracting it. So negative 2 comma 5 plus or minus 7, but don't leave it
Don't leave it like that because we can... Now, if that said plus or minus the square root of 7, no problem. But we can, all of us, do 5 plus 7 because we can just count on our fingers, and some of us just our toes.
Just our toes to get to 12?
Some of us need all our teeth. Yeah, you know. Why are you looking at me like that?
No reason.
Maybe I
the
have,
foci, so we need c. So we do a squared minus b squared. And what may happen to you occasionally is you'll put this in and you'll get a negative that you have to take the square root of. That means you put them in the wrong order. So that's 49 minus 9, which is 40.
So the square root of 40 then would be your c value. And that's the distance from the center to the focus.
Right, and so if I square root this and then simplify, that would give me 2 square roots of 10.
Wow.
Because...
You simplified it. That's pretty good.
Because it's 4 times 10 and you can take the square root of 4.
Square root of 4 is 2.
Yeah, so foci. And this would be the case where we could just put plus or minus 2 square roots of 10 and leave it because now we don't have like terms.
Right, right. We don't have things that we can put together. You're correct. So center, focus, and vertices. All right, good job.
All right.
Eccentricity.
That's...
and not of rich people.
No, that's a different kind of eccentricity. So eccentricity we label with an E, and it is C over A, which if you don't know what C is, then you would go about it using your nice Pythagorean relation.
Hey.
And what it is it's a way for us to kind of categorize how stretchy, yeah, for lack of a better word, an ellipse is. And so and it says over here to the side, if your E value is 0, what you actually have is a circle because it's the same both directions. And we don't have a separate section for circles because circles are they're ellipses. Kind of like all squares are rectangles.
Right. What?
All squares are rectangles.
Since when?
Forever.
Oh, I've been living a lie.
Yes. So the closer you get for your E value to 1, the larger the difference between your major and minor axis are going to be.
Is it hot in here now all of a sudden?
I don't know. So on example 5, we're going to talk about what we were talking about a second ago about the Earth's orbit, that it's not actually a circle, it's an ellipse. Now, it may kind of be close to a circle, but it's actually an ellipse. So it has a semi-major axis. A equals 149.598 gigameters, which is like a cool unit.
A million meters?
It could be. How much is a gigabyte?
A million bytes?
Then it has to be a million meters.
It's a million megabytes. I don't know.
I don't know either. And an eccentricity of E equals this number.
So he's not very eccentric.
No, he's very close to a circle.
Yeah.
So, and the closer to a circle you are, the closer in your foci are. So our foci are actually really close to the center.
Yeah, they're not far apart at all.
Yeah, so calculate and interpret B and C. Well, if we know what A is and we know what E is, we can find C using this formula, and then once we have C, we'll use the Pythagorean relation to find B.
Sounds great.
So 0.0167 is E. We want to find C over 149.598. Oh, do you want a calculator or?
I got a calculator right here. So that's going to be 0.
So we'd multiply those together to get C.
Times 149. I got that number right there.
2.498 gigameters. Thank you. I got it. Thanks. Okay.
Right.
So that's C. Now let's interpret what C is. What is C normally?
That C is the distance from the center to the focal point.
Ooh. The distance from...
So the center of our...
Center...
The center
of the orbit.
Of the orbit, yeah. Which means that...
To each foci.
Right.
So we just said that, it's circular. It's pretty circular, so that means that it's the foci are really close to the center, but very close to the center. It's still 2.498 gigameters.
I don't even know what you just said right now
pretty
because
far.
I have a hard time talking about 2.498 million miles. So
yeah, that's quite a situation to have. So then our B, we're going to use our Pythagorean relation for.
Well, now we have A and C, so.
Yeah, so our Pythagorean relation was a squared minus b squared equals c squared.
Right.
So 2.498 squared equals a, which was 149.598 squared minus b squared.
Oh boy, that's a lot of stuff going on there.
So, I mean,
you're basically trading b squared in the 2.498 is what you're going to do.
Yeah, you're
and then take a square root.
You want to...
Well, there it is right there. I couldn't even punch that in, but we happen to have it.
So after square
located.
rooting, you should end up, and I could have just plugged it into this formula as well. C equals square root of a squared minus b squared, but we still would have had to solve. So B is 149.577 gigameters.
Oh.
And so what is B telling us?
B is how far from the center of the orbit we go to get to that edge, the upper or lower edge.
Okay, so
it's the semi-major.
The distance. Isn't it the distance to the closest point in the orbit?
That's probably a good thing to say, yeah. I like how you said that.
And speaking of which, what were those words you were saying earlier so that we can define them really quick? These may come up at some point, so...
there is perihelion.
Perihelion, is that right?
Yeah.
Okay.
I'm not sure how
A perihelion is something to that effect is
closest
what you should see.
point to the focal.
Closest point to the focal?
To the focus, yeah. Closest point to the focus.
To a focus.
A particular single focus. So we're talking about just one focus for the whole thing.
One or the other focus?
One or the other.
And then...
aphelion, APH, and then the elion. These sound Latin.
It could be.
Do we need to go find Miss Turner and get some Latin?
No, let's just keep going.
So
that's the farthest.
So if we talk about the same focal point, now we're not switching focal points, but if we talk about the same focal point, now this is the point furthest from.
Okay. So closest point, the distance to the closest point in the orbit, this was from the center.
Yeah, that one's from center.
Because we're talking about
right.
B.
And these are from focus.
Okay, so that may come up in a problem or two, so now you know what the perihelion and aphelion are.
Exactly.